Hey guys, what's going on? So today we are going to be going over homology. This is all within the context of Chern-Simons theory. I want to go over some algebraic topology, which is as sort of a prerequisite before we dive into the Chern-Simons stuff and the electromagnetism, which is why we're covering homotopy, homology, and cohomology. So with that being said, make sure to hit that like and subscribe button. You can go onto my Patreon page to support there, or you can become a member here on YouTube and support that here as well. Okay, so let's go ahead and get started. At the forefront here, I also want to mention that if you contribute, you'll be able to get full videos. Okay, this is just going to be a partial video, and so just keep that in mind. Alright, so we are talking about a final look on homology. So it's been a while since I posted stuff on Chern-Simons theory, so we're going to recap just a little bit, and then we're going to go from there. Okay, so like I said, it's been a while since I posted anything on this, so we're going to recap. Previously, we had introduced the concept of homology. So homology, we found out, was we had these simplexes, or the simplices, existing in this space Cn, okay? And we talked about all the things that could be boundaries within this space, all the simplices that could be boundaries within the space, and then all the things that actually were boundaries in the space. And what we want to do is we want to take the quotient of these, right? So we want to take all the things that could be boundaries inside the space, but quotient out all the things that are boundaries already, okay? The reason we want to do this is because then we get non-trivial topological objects, okay, within these spaces. So thinking about this schematically or diagrammatically, we have this space Cn, and Zn is all the things that can be boundaries. So so if we're looking, for example, at a shape like this, well, if our simplex is, if we're looking at C3, right? The C3 is going to be a three simplex, or a three simplical complex, however you want to say it. It's going to look something like this, maybe. And its boundary is the purple thing, right? The boundary is the purple thing. We want to be able to find the things that are, they could be boundaries, right? They could be boundaries, but they are not boundaries of anything, right? So this thing is a boundary of something. This purple thing is a boundary of this. We want to find things in this space, right? In this space where n is 3, that are boundaries of something. They are boundaries of something in here, but they themselves are, they could be boundaries of something in here, but they are not boundaries of anything else, right? So we can define our homology group to be the quotient. So we're quotienting out this thing, right? So these are all the things that could be boundaries. These are all the things that are boundaries. So when we quotient out all the things that are boundaries, what we're doing is we're saying, here's this group of all the things that could be boundaries that are boundaries, and then we're going to take all the things that are boundaries out, and we're left with all the things that could be boundaries, okay? And the idea here is that, again, these things are non-trivial. And these things are going to help us understand the topology of our space. And in the end, it's going to help us understand holes, okay? How we can count holes in our topological space. So visually, again, we can think of this as taking all the things that could be boundaries of something, but taking out all the things that actually are boundaries, right? So topologically, we're interested in this situation because then we have a non-trivial loop. So there's nothing in here, right? This thing could be a boundary, but there's nothing inside of it. So there's a hole inside of it, if you will. And so this idea is that we don't want this, right? We don't want this. This is something that actually is a boundary because there's stuff filled inside of it. But we do want this, okay? So how do we get this? Well, we use this prescription. Okay, now we're going to go through some examples through here. But one thing we also want to make sure is that visually we can think of this as taking all of the things that could be boundaries out of something, but taking out the things that actually are boundaries. Naturally, we can see this or see that the space of all things that can be boundaries is larger than the space of all things that actually are boundaries, and therefore we can say that all the things that could be boundaries is a larger space and incorporates all the things that actually are indeed themselves boundaries. Okay? And what we're going to find later when we start talking about cohomology is that when we quotient this thing out, what we're actually doing, there's a deep principle of set theory, if you will. It says when we do this, we're actually finding equivalence classes inside Zn. So we're going to find all the things that could be boundaries, but at the same time, when we do that, we're going to find things that are equivalent to each other upon doing this quotient. Okay? Well, we'll get there. All right. So let's do an example. Our first example is this just P0. This is just a point. This is a zero simplex. Just a point again. It lives in C0K. Right. So our complex, if you will, our simplex is named K. It's just a point. Its chains. Right. So the chains again. These are the coefficients on each point, because we want to treat these as a vector space. We talked about treating simplices as vector spaces. When we did that, just recapping, we talked about, say we had points, and then we had boundaries. We had boundaries on those points, and then we filled in that, well, for C0 of K, and then we had blue, we have C1 of K, and then green, C3 of K. And I'm going to reduce the thickness of my pen here. Make sure I have some space. In this thing, right, so in this guy, backwards, just this is a backwards thing, but the idea here is that we have C0 on P0, right? So we have P0, and then actually we don't want the brackets to be technical about this, because the brackets indicate the entire set, and then this is going to be P1, it's going to be P2, and then this line is going to be P0, P1, this line is going to be P1, P2, and then we want the brackets, and then this line is going to be P2, P0, right? And then these things also have an orientation, so this is going to go like that, it's going to go like that from 2 to 0, and then from 0 to 1, and so our orientation of our 3 simplex then is, if we label this guy, that is going to be P0, P1, P3. That's our simplex. All right, and so this is all a recap, but it's nice to do a recap, right? Because we don't want to forget this stuff. Inside here, this is a vector space where we have C1, P1, and then plus C2, P2, and then in this space we have C. This is just a constant, but we'll call it 0, 1. Okay, and then we have P0, P1, plus C1, 2, that's going to be P1, P2, and then plus C2, 0, and that's going to be P2, P0, and so forth. And then this thing is going to be C1, 2, 3, right? And then this object is P0, this is 0, 1, 2, right? We always start at 0, so P1 and then P3. So these things, this is our 3 form, or not our 3 form, this is our 3 simplex. There's going to be I said form, right? There's going to be this duality between forms and simplices, as we'll see. And that's when we start talking about cohomology. But these things are our lines, right? And then these guys are our points. And we make the stipulation, we've made the stipulation that the constants Ci, sum over I is equal to 1. Same thing here. Cij, sum over Ij, that's equal to 1. And then our constant here has to equal 1 as well. So Cij, K, Ijk equal 1. Anyways, so that's just all a recap. Anyways, let's get back to this example, and then we'll sort of fly through this. This is probably going to be somewhat of a longer video, just because we want to get the homology done out of the way. Then we'll start talking about cohomology. So obviously, this thing is going to be 0 for any C and C0, because it's just a point, right? And so Z0, I'll say Z, Z0, K, and C0 of the simplex, they're equal, right? Because again, this is just a point, and so this is everything that could be a boundary. So points are the only things that could be boundaries, because we're literally just looking at the space of points, and this, or the space of points in our the space of simplical points. And because there's no C1 of K, we take the boundary to be 0, so we mod out 0. And so this thing here is, this is important actually. So this is going to be true for all of the CNs, right? They're going to be isomorphic to the integers, because we're able to add them up like we do with integers, add and subtract them up like we do with integers. With cohomology, we're going to be looking at R, right? Because we're going to be looking at forms, and forms are going to have more, they're going to be isomorphic to R. We'll talk about that later in cohomology, but that's going to be a big difference that we want to talk about also later. Okay, so let's take another example. So this is example 2, right? Because this was example 1. So example 2, right? So example 2, we have these guys, right? So these are our points, these are our lines, and this is our area. So we kind of talked about this already in our recap, so we might be able to fly through this a little bit faster. But the idea here, okay, is I've labeled all of them. I've labeled my points, I've labeled my boundary, and I've labeled my the 3, I always want to keep on saying form. This is our 3 simplex. So when we're looking at C0K, this space, it's going to consist of elements C, such that we have this here. So C is an element in our space. We can write C as, just like we did here, I just have different coefficient names, but we have A, B, and C, where A, B, and C are complex numbers, okay? They can be real numbers, but we want these to be complex. And we want to find all the objects that could be boundaries in this space. So we use the boundary operator. So if you recall, the boundary operator is this thing. And so it's going to act on this, and this is by definition is going to give us 0 because because these are boundaries. These are just points again. So to find the things that are boundaries in C0K, we need to perform the boundary on objects and C n plus 1 of k, right? Because when we look back up here, we're doing this part right here. We're doing this, right? Because we can also, the same process as this right here. So we d n plus 1. So these are actually, so we're actually doing this, right? We're actually doing this. So, and okay, so when we do that, we have all of this then, right? Because the boundary of P0, P1, that's going to be P1, P0. Again, this takes into account the directionality or the orientation of our form. So we have all this, and then we have this. We can, this is just some algebraic manipulation. And then from here to here, then we redefine these guys here, and we could see that d prime minus e prime, right? So this minus this is going to give us this. And so rearranging this, we get this right here. This means that an arbitrary element of things that are boundaries, right? So in here is this, right? Because this here, that's right here, that's right here. And then f prime is this guy, right? Because we said f prime is d minus e, right? So, okay, so this is where sort of the things start to click, hopefully. So in Z0, we have this object. In B0, we had this object now. So we use this function f. All right, we won't go too deep into this. This is a principle of homomorphisms, but the idea here is that we can use this function f to take this object, right, and this object is going to spit out a number, right? So and the number is going to be the sum of the coefficients, right? This isn't quite obvious why we're doing this, but we'll see why in just a few seconds here. So any element in the kernel of f then, right, the function f takes this thing, brings it to a real number, which is just the sum of the coefficients. The kernel is going to be when this equals 0, okay? So that's this. And then we can see that c is equal to minus a plus b. Well, this defines exactly an element in B0 because it takes the same form here, right? Because this is minus the sum of these two. This guy is minus the sum of these two. So we found this f. If we can find this f such that it maps our simplices to just the sum of their coefficients, then indeed we have we are now able to mod this out. And when we do that, we get that if we mod out the kernel of f, right? Because that's what we did, right? So we did the kernel of f brought us to something that looked like an object that was in B0. So when we do that, then we get the image of f. Okay, that's the image of f, and when we go from here, okay, and we get this z, this z group. Okay. This is all to say that if we take, so we started with this object, okay, and for C0, we got this. For 1 now, we are going to get, so here's Z1, here's B1, we do the work again. So we have this object here, right? These are all of our all of our lines. We do the same thing. We have coefficients. We define the boundary of those. The boundary of those is going to be this, okay? Again, that takes into account the directionality, these minus signs, and then, or the orientation, whatever you want to call it. We get this. This is the boundary when it is 0, which means this. Okay? So when this object is 0, we can conclude this. And so so we get that this object here is in Z 1 of K. Okay, so because A equals B equals C, so we don't need these coefficients, right? They're all just the same thing, okay? So we just set them all to 1. We could do that. All right, for the things that are actually boundaries, so these are the things that could be boundaries. The things that are actually boundaries, well, we have, we do this, right? So when we want to take the boundary of this 3 form, well, it's going to be this guy right here, okay? Well, this is just, we can reverse, right? So we have P1, P2, here's P1, P2, just highlight these, P1, P2, and then P0, P1, P0, P1, and then P0, P2. But these guys we've swapped, right? 2 and 0, 0 and 2. The reason, and then when we do that swap, we get the we have to change the sign because again these things have orientation to them, and so the structure of the elements in each space is identical, right? Because we have this object, no coefficients in front, and we just have this one coefficient in front here, or we do that, right? We have A and we have D, so the structure of these are completely the same now, which means that we're left with the identity element upon calculating the homology group for the lines of our triangle. So when we mod these things out, this is really just like when we mod this out, everything here has the same form as in here, so we're modding everything out. So that means h1 of k is equal to 0. Okay. So we had h0 of k, and we had h1 of k. Okay, h0 was z, and h1 was 0. Oh. All right. So note that if we do not include the area in our original set, then there's going to be no 2 simplex. Okay. And there'll be nothing to take the boundary of it. So we have to do this then. These are all the things that could be boundaries. This should be 1, right? This should be 1. And we have to mod out 0 then, and we get z. And this is because there's no b1, or there's no we don't have this thing, right? We don't have this thing, so we can't do this, and so we have to mod out. So we mod out 0, and what we get is this. And this is interesting, right? Because let's take a look at this picture. Notice that when the space is filled in, we had h0 equals z, h1 equals 0, h0 equals z, h1 equals z. So it seems like every time there's a hole, or something where there's like no area that's being encompassed, then we have this z, right? So the hole, so when there's a hole, this is specifically a one-dimensional hole. This is what this 1 is going to refer to. This one-dimensional hole, we get z. So this is counting holes, and every time there's a hole, we attribute z. Okay, that's the way we want to think about this, sort of in the simplest terms as possible. Is that this homology group is going to count number of holes, and the number of holes, when it counts, it attributes z to the hole, right? So if you have some object like a 3 torus, let's see, if you have some object like a 3 torus, well, we're going to have z, and z. So it's going to be, we're going to have 3 z's. We'll see how we write that. I have a diagram up here. All right. And we can infer this from that. We can infer that from the homology of H n of k, this looks for n-dimensional holes and will assign the space of integers to each one. All right, so I'm going to stop here for those of you who are not contributing to the channel, because I want to give those of you who are contributing to the channel some extra content. So with that being said, I'll see you guys in the next video, and bye.